All right, so the proof of the theorem that I was just talking about is going to require some understanding of monomorphisms. In particular, it's going to require some understanding of when monomorphisms are linearly independent in the linear algebra sense. Okay, so let me just remind you that if L over K is an extension, um, let's see, how do I want to say it? I want to say, actually, not that. Let me just say it like this. If L over K and M over K, yeah, I'm going to change the notation in a little bit, are extensions of K, then M and L are K vector spaces. Right? That's how we motivated things like the degree and whatnot. So the collection of linear maps, which is sometimes written HOM from M to L, and all this is it's a collection of maps from M to L such that T is linear over K. And reminder, that just means that T of M1 plus K M2 breaks up as T of M1 plus K T of M2 for all K and K and for all M1, M2, and M. This is a K vector space, actually. Why is that? Well, we can go ahead and add linear maps. So if we have two linear maps in this set of all linear maps, and we have some little k and k, then it's routine to check that S plus little kt of M defined by, so this is a definition, S of M plus kt of M defines a K vector space structure. And you see this in really in any linear algebra class. All we're saying here, if we were to write this as matrices, is that it's possible to add two matrices and still get a matrix. And it's possible to scale a matrix. So if K is 1, right, if K is 1, we're just adding two matrices. We still get a matrix of the same size. And if S is 0, we're saying it's possible to scale a matrix by a constant. That's all it's saying. So that this is a vector space is not mysterious in any way. However, if we have monomorphisms, so if mu and lambda from M to L are monomorphisms, which, remember, to be a monomorphism, that's a field theoretic property. You not only have to be a linear map, but you also have to obey the field structure. Then what we're going to show is that the only way for mu and lambda to be independent is if they're equal. So then mu and lambda are linearly dependent if and only if they are equal. That is, when we impose this additional field structure, we get linearly dependent maps if and only if they're just honestly the same function. Now, this is not true in general. For example, if I had one, so in general, without the field structure, it's possible to have two just injective linear maps that are linearly dependent. That are dependent but not equal. I'll give you an example. All right, let's consider the identity, which is that we can represent as a 2 by 2 matrix, which we could think about as a linear map from any two-dimensional vector space to itself. And then we're going to do 2 times the identity. That's another linearly independent map. Another injective map from the vector space to itself. And certainly -2 times the first map plus 1 times the second map is 0. So we have a linear dependence of these two. And what's special? Well, although the identity happens to be a field monomorphism, twice the identity is not a field monomorphism. So let me just label that, maybe in orange. This one's a field monomorphism. In particular, it's also a linear map. This one's just a linear map. That's what's going on here. So when we impose that they also have to respect the field structure, we get that they're dependent if and only if they're equal. And that's something we're going to elaborate on in this chapter. In the next video, we're going to prove it in the case when n equals 2, and then we'll go and set it up in the general case.